Hello, my name is Alvaro Cabrejas Egea, and my project is Honorary Project 11, Optimizing Flow within Mobility Systems with Artificial Intelligence. In this project, we have Alan Wilson as PI. Then they're also collaborating. We have Luis and May, who are our in-house software developers, that they will be most needed for later stages of the project. And the main project is split into two different parts. The first one will be Damon Wishik working on knock-on effects on systems of systems. And the other one where we have Neil and myself, where we're looking at artificial intelligence for urban traffic control. So the first project, the knock-on effects on systems of systems, essentially looks at unintended effects of interventions in our mobility network. And some of these can be highly counterintuitive and even sometimes paradoxical. So that's why I included a couple of examples. For example, if the city lowers the bus fare from A to B, the passengers move and start using the bus service, but then Uber will realize that their fleet is not getting as much traffic as before, so instead they will rebalance their prices, driving them down. And actually, the net number of bus passengers in the long run will go down. Another example of this is when we have the city center completely congested, we tweak the accesses to the city such that less cars will have it more difficult to come in quickly into the city, hoping that this will drive traffic towards public transport. But in the end, what we achieve with this is that buses start circulating more slowly, the bus passengers realize that there is some extra cost in terms of time in taking the bus, so they start taking their own cars, and in the end we generate even more congestion. As with other bits of the project, this will become even more relevant towards the end of the project in about 18 months' time. From our side, well, the UK has been historically on the leading edge in terms of urban traffic control. The first traffic light was installed in London. The first electric traffic light was also installed in London in 1926. And London is also housed to the SCOOT system, in which one single controller will control one or several complex intersections, effectively managing all of the traffic signals at the same time. What we aim in here is to develop the next generations of such systems in a way that they are automatically managed, that the system manages itself. In order to do this, we have been working with a simulator which is called Sumo, a simulator for urban mobility, and we will have as our agents the individual traffic lights that will be learning from the traffic conditions, taking their own decisions, and through a feedback loop, well, getting better and better at doing this. We will do this obviously from a reinforcement learning point of view, in which, as I said, the traffic light will be our agents, and our decisions will be the red and green phases in an intersection in each of the directions possible. So, as any reinforcement learning framework, we have our controller, which in this first iteration is the table. We will later on move on to using neural networks. The agent exerts one action over the simulator for which it gets rewarded, essentially based on the positive or negative effect that such action had over the system. Then the system will spontaneously evolve. The system will be then again observed by the agent, which based on that observation and the incorporated knowledge through the reward, choose the next action to do. The learning algorithm that we've been using for starters is Q-learning, because it's very basic. You just have one table with all of the potential states that your system can be in, and your columns are the potential actions that you can take. The main limitations that we have is that, well, the dimensionality of your problem, because essentially very quickly your table becomes untractable, and you cannot visit enough times each of the different states to meaningfully learn something from them. It's worth saying about this that the agent does not know anything about the environment. They don't know what a traffic light is. There is no prior knowledge included. This algorithm, through its hyperparameters, is capable of handling exploration versus exploitation. And it also can look beyond the immediate future, beyond the action that you're taking, but you can have an idea of where will you end up a couple of actions down the line and optimize over the long term as well. So in order to define our state space and our action space, well, first of all, for the state space, we measure which queues do we have in the north and south orientation, then the queues on the east and west direction for each one of these intersections, and which, in the case of having several traffic lights, we will see what the neighboring traffic lights are doing. This already creates fairly big tables, which take some time to fill. And for the actions that we will give, they will be fixed green time programs, such that we will pick one green time for the north, south, or east-west orientation. It doesn't matter which one you pick first, but you pick one of them, you assign them the intergreen times and a total cycle time, and the other green time will be the total time. This is actually wrong because it should be -6 to include both of the intergreen spaces. Yeah. So this alone, for the case of having one single neighbor, gives you a table which has 3,025 state action pairs, which is already quite big to explore, but the results are quite promising. Yes, there it goes. Over here, we can see the untrained controller, so no prior knowledge, and it's simply trying to assign, it's learning, by the way. As you were seeing, it plays learning, but as you can see, it's not great. The color coding that you can see, green is painted red if it's moving, yellow if it has been waiting for less than 20 seconds, and red if it has been waiting for more than 20 seconds at its current stop. So as you can see, we are able to create some waves, but it's not able to replicate them systematically, and these will become relevant in the middle stages of the project, in which we will attempt to create dynamic green ways throughout the city. So for example, if you're entering from the north, what you want to go is get in the road that will take you closer to your destination. The controllers identify that you have a high road, so it will be all green for you. I believe that this is the already trained controller, and you can see that with some errors, like you could see in the middle over there, but mostly over here, under the exact same demand, the whole intersection is way less congested, and again, you could see another error over there, but these green waves are mostly achieved. This is not something that we have told the algorithm to do. This is something that it discovered by itself, and it seems to be working quite well. However, we need to look how this scales with more intersections and more complex networks. Some results, this is, over here we have the queues in each one of the directions, and the big graph is the reward that we will be giving to the system. Actually, this one is just the negative sum over all of the queues. So what we want for the system is to have no queues whatsoever. If we move to the train controller, and there again for comparison, you can see that at the beginning there is a fairly steep learning, and then it keeps oscillating, but mostly going forward. For the train controller, we can see the oscillations. These 5 areas are 5 different regimes of demand. So for some of them, you just have more cars incoming. So whenever you approach the theoretical capacity limit of your intersection, you're not going to be able to absorb that traffic no matter what you do. So that's what we're seeing in these random spikes. And in general, you can see that all the queues length decrease quite a lot with the train controller, and in general, it is showing a promising, it looks promising for the next 12 to 18 months. So looking forward from now on, we've been using some open source simulator, which works well, but it's not very flexible and not everything that we need. So we're transitioning at the moment to PTV's vSim software, which is a industry-grade microscopic simulator. Is what they use in Transport for London, Transport for Greater Manchester. Essentially, all the major players use this software. We will soon be visiting the Transport for Greater Manchester control room for a week to learn what it is to actually manage transportation on the great scale. We are trying to get a complete model of London from TfL, and we're talking with different companies and stakeholders for all of this to to essentially try to create a big collaboration group and have the Turing as center of it. Other than this, from the point of view of theory and control, we will be moving to more sophisticated control methods. Essentially, we will be using machine learning to estimate the value function that we're trying to improve. And that allows you to deal up to a degree with the curse of dimensionality, so we will be able to feed it more data. I at least want to try the Scoot approach if the value function approximation works, in which having one single controller, you try to control several intersections and essentially define an area which you will then try to optimize globally. And then for the last bit, and this will be in about 1 year time, we will want to look at how these control systems interact with the dashboard, with the incident, the dashboard to deal with incidents and essentially define interventions and see how it ties on in the grand scheme of things. That was it. Thank you very much. Any questions?